Welcome back. In today's video, we're going to talk about surface integrals and apply some of the same ideas that we learned with line integrals, but now kind of mixing it up a little bit and changing some of the formulas that we work with to adapt them for working with surfaces instead of lines. So as the name would suggest, this is integration on a surface. And it looks like this. It's a double integral because we're working with an area. It's a surface area here that we're working with of f, and then we have d capital S. So if we kind of want to break this down a little bit, just kind of look at the notation in particular, we have a double integral because we are working with a surface, which is area. So you've got two dimensions going on. And then I do want to point out that that is a capital S as opposed to a lowercase s that we had with the line integral because we're working with surface area, little pieces of surface area instead of little pieces of arc length. Okay, so like I said, this is kind of the same idea as earlier that we had with the line integral. So and we think of f as a density. So maybe, for example, you can think about it as mass. Instead of per unit length, now we're going per unit area. And this is going to be multiplied by little pieces of surface area. That's what the ds is. And then adding them all up. And that's what the double integral does. Okay, so what that means, though, is that if you ever wind up with a function that is just simply equal to 1, then just as taking a line integral with a function equal to 1 gave us the length of the line or the length of the curve that we were looking at, what we're ultimately going to wind up with is if f is equal to 1 and we look at this integral, we're going to wind up with just the total surface area of the surface we're looking at. So if we have double integral over that surface S, f d capital S, the way to interpret this, or the way to write this out would be to do double integral over S and then multiply by 1 ds. And the way that we read this integral here, this chops the surface up into little pieces. And the double integral adds them up. And since each of the little pieces is only getting scaled by 1, well, we're not really changing them any. So all we've done is take our surface, chop it up into tiny little pieces, and then added them back together. So what you get at the end of that is just the surface area of your objects. Okay, whatever that surface S was that you started with, that's what you get when f is equal to 1. Now, if it's not equal to 1, it's giving us this notion of density that we've talked about here. And ultimately, you're going to wind up with like mass or charge or whatever is on top there. But yeah, when f is equal to 1, we get this idea of surface area. Okay, so I mean, that's kind of all about the intuition behind it, what it tells us and all of that stuff. But I mean, you guys really want to know how to compute it, right? So let's look at that. Okay, so how to integrate. Step 1 is going to be to parameterize S, and a lot of times this will wind up using cylindrical and spherical coordinates. So don't be afraid to reach back and use those as well. And we'll look at some other techniques for parameterizing surfaces as well, but this is just a couple that you want to keep in mind because they will pop up again. And then the next piece, which is actually the formula that we're going for, our double integral over S f ds is equal to the double integral over a domain D, and I'll tell you what that is in a second. F of a parameterization of the surface, which is RUV, times the length of N of UV, du dv. Okay, so let's break this down. What is in here? Okay, so in this case, our parameterization is R of UV. And notice that it has two inputs instead of just like the standard T that we normally use. And this is just simply because we have a surface, we're looking at area. So we need two inputs to account for those two dimensions that we're hoping to wind up with. So. Which means, so since it's surface, what you wind up working with is area. Okay, D are, this is just gonna be the bounds that you found for U and V. And then finally, this guy right here is new, but it kind of holds a similar place as R prime did when we worked with line integrals. Okay, so N of UV here, which we take the length of, is just equal to RU cross RV, where this right here, that's just your partial derivative with respect to U of R. And then same idea here, partial derivative with respect to V of R. Okay, so just as I was with the line integrals, a lot of it is figuring out how to parameterize your surface, and then after that, it's really just plug it into this formula right here, and you are good to go. So, but before we jump into working with this whole integral, I do want to work a couple of examples that take parameterizations that do not depend on cylindrical and spherical coordinates because they are a little bit tricky. So a couple new ways to parameterize. Okay, so here's an example. And this also kind of like introduces the way to parameterize. If we have a graph z equal to some function of x, where x is between a and b in the xz plane, then just generally speaking, this particular line right here gets parameterized as R of t equal to T0 G of t. So this is the same idea as what we do when we have just like a function when we're looking at a line integral, but instead of working with this y component here, we're now looking at working with the x or the z component. And again, t is bound by the same things that x is. Now, this isn't a surface, this is just a curve. So to actually get the surface that we're interested in, we rotate this curve around the z-axis to get a surface that we're actually interested in, and parameterize it as R of UV equal to, now we're going to get U cosine of V, U sine of V, and then G of U, where U is between A and B, and V is between 0 and 2 pi. Okay, so that probably maybe looks a little bit random, but I'm going to do a more concrete example of this in a little bit. But I will say this is definitely something that you should kind of have either highlighted or marked in some way to denote that this is a method of parameterization. Okay. All right, so let's go ahead and use a specific instance of this. So for this one, we will find a parameterization for the surface created by rotating the curve z equal to x cubed, where x is between 2 and 4, around the z-axis. Okay, so if we refer back to this right here, I'm going to kind of summarize what we're going, and then we'll draw a picture of what we're doing as we do this, so that way it can be kind of clear to see how this all connects. So the first step is going to be to just parameterize the curve in general, just the way that we know how. And then the second step is going to be to worry about rotating this around the z-axis to produce this new two-dimensional parameterization instead. Because here's what we're looking at. So if we have all right, so there's our axes. Let's go ahead and do this in, let's use pink this time. Okay, so the curve z equals x cubed. It looks something kind of like this. Okay, and it's strictly in the xz plane. Okay, so it's not anything in the y direction. It's just, imagine it flat against the xz plane. And the part that we're interested in is the part between 2 and 4. So x equal to 2, x equal to 4. This is clearly not to scale, but this is kind of the idea. So this is the segment we're looking at, is this piece right here. Okay, we want to parameterize that, is step 1. So we need to write r of t is equal to, well, we just replaced the x with the t, and then we get 0 because there's nothing going on in the y direction. And then we have t cubed here for z. And t is between 0 and 4. Okay, so that's just reflecting, or 0 and 4, 2 and 4. That's reflecting the fact that we're on this line segment and we're looking to go up like that. Okay. Now, what we ultimately want is going to be the surface created by rotating this around the z-axis like so. So if you kind of remember back to, I think it's Calc 1 that you typically learn surfaces of rotation in, this kind of goes back to that same idea where we're taking this, we're swinging it around the z-axis, except I guess in this case, we really just want this piece down here because we're only going up to 4. And we're looking at this particular curve. It's slightly bowl-shaped, and we only want the surface. We don't want anything on the inside of it. We just want the surface of it, okay? So that's what we're looking to parameterize. And in order to be able to do that, I mean, we take this formula. We've got the r of uv equal to, well, I can just kind of plug it in, u cosine v. This is just looking back at this right here, u cosine of v, u sine of v, and then the z component really just stays the same. We swap out t for u. And then, oops, that should be a u. Okay, so, and then in this case, we have u going from 2 to 4, and then v goes between 0 and 2 pi. So why? Why do we have this? Well, the reason behind this is that if we look at, say, just like a little cross section of this, like so, okay? This is a circle. And this particular little circle has a radius right here. Okay, and this little circle is what we're kind of parameterizing with this u cosine v, u sine of v. Okay, so if we just kind of focus in on that, this is the parameterization for a circle of radius u. Well, u ranges from 0 to, or from 0 to 4, 2 to 4 here. And so that's kind of saying, okay, I want my radius of my circle to go from 2 and then eventually make it out to 4. And since u here is kind of acting like my x value, that's why it winds up getting plugged in here in my third component. But ultimately, you wind up with these circles that get stacked vertically according to the height given by the value of this curve here. So we're kind of taking all these circles and stacking them together along this line segment here. And that's really just what is happening in the parameterization. So we need to think about this. this right here is a circle with radius u and height. And when I say height, I just mean like how much it's been lifted up above the xy plane, u cubed. Okay, so it's kind of sliding up and along this curve right here, where its distance from the axis is determined by how far out this curve goes, and that's really just what u is. So, okay, but anyway, that's really all there is to that problem. You just have to, if you want, you can just walk through these steps, and then you get that right there. And this is your final answer, but I just kind of wanted to justify geometrically for you where this formula comes from. So, okay. And I know one thing that's kind of popular is to use, you can use other letters if you want for your parameterizations. As long as you do not get your notation mixed up, you can use whatever letters you want here with the U and the V and stuff like that. So we'll run into some things later. I will always use U and V, but maybe you might find it easier to stick with the standard theta or phi or whatever you have. So, okay. Let's work another example that kind of looks like that. So in this case, we're going to have just a slightly more complicated version of it. So if we have a curve of the form r of t equal to f of t, 0, g of t, a less than or equal to t less than or equal to b, and rotate it around the z-axis. So again, we're working with a surface of rotation, but it's just a little bit different structure this time. We parameterize it as r of uv equal to, and we'll have this same idea here that we had earlier, where what's in my x component is going to become my radius. So f of u cosine v, f of u sine v, and then you get g of u. And then u gets to be between a and b. And v is between 0 and 2 pi. Again, this is because we're rotating it all the way around the circle. So now we're going to use this to find a parameterization for the surface created by rotating the circle x, y, z, such that x minus 4 squared plus z squared is equal to 4, y equals 0. So this is just a circle in the xz plane around the z-axis. Okay, so to be able to do this, our first step is to write this parameterization right here, and then we just turn it into this parameterization right here. Okay, so r of t, since we have a circle in the xz plane, well, we're just going to parameterize the circle the way we normally do, and then our y component is just 0. So to parameterize the circle, radius 2, cosine of t, and then we'll have plus 4 to account for the fact that we've moved it over 4 units, and then 0 for our y component, and then 2 sine of t for my y component there. And because this is a circle, t is going to be between 0 and 2 pi. Okay. Now we just get to do this line right here, which is ultimately what we want. So this is going to be, this piece here is going to go in front of a cosine v, and I'm swapping out t for u. And then we have 0, and then we have, or not 0, I'm sorry. This will be 2 cosine u plus 4 times sine of v. And then my third component here is just 2 sine of u. Again, the z component, you just take the same thing that you had there, replace the u with the t, and you are good to go. And u follows the same bounds as t, so u is between 0 and 2 pi. And v, because it's going all the way around the z-axis, has to be between 0 and 2 pi as well. Yeah, so that's just a couple of new options for how to parameterize curves. Again, maybe kind of mark this if you're taking notes as being another formula for parameterizing things. So a lot of these two both have 2 steps. First, you parameterize the line, and then you parameterize it as it has been rotated around the z-axis. Okay, so let's get into taking some surface integrals now, putting all the pieces together. So with this example, we will compute the surface integral over S f ds when S is our surface x, y, z, such that x squared plus y squared plus z squared is equal to 16. So notice that this is equal to 16 and not less than or equal to 16. If it were less than or equal to 16, we would get the inside of the sphere. But since it's equal to 16, we only care about the outside of the sphere. So it's just kind of like a balloon that's been blown up, basically, is the way to think about that. Okay. And then in this one, we're going to have our function be identically equal to 1. Okay. So we're going to use our formula. Double integral over S f ds is equal to double integral over a domain D of f evaluated at a parameterization of our surface, RU of v, and then times the length of this vector in UV, and then du dv. So to be able to do this, first thing we want to do is parameterize our the sphere that we're working with, and this is where we're going to use spherical coordinates because we have a sphere. And the way to do this is, I mean, like we're going for something that's got 3 components in it, right? We're looking to fill out an x component, a y component, and a z component. And the way that we do this is we're actually just going to use the same identities that we've used for spherical coordinates all along. So x is equal to rho sine, and I'm going to use v for phi and u for cos or for theta. So where v is getting mapped to is the same thing as phi, and u is representing theta in this case. Y is equal to rho sine v, sine of u, and z is just equal to rho cosine of v. And if we look at this right here, this gives us the information we need about rho. So rho is going to be equal to 4 in this case. So to parameterize this, each of these is just going to become my components. So this is my x component. It'll be 4 sine v cosine u, 4 sine v sine u, and then 4 cosine of v. And that's pretty much all there is to parameterizing this. And then we just need some bounds on u and v. And since we're looking to take an entire sphere, v, which is representative of phi, is allowed to go from 0 all the way down to pi. Oops, that should be a v. And then 0 is less than or equal to u less than or equal to 2 pi. So because we want this to go all the way around the z-axis the way theta could, so that's going to be 0 to 2 pi. So this is our parameterization. Now we need to compute this piece right here. I'm going to need a new page to do that. So we recall that this is equal to RU cross RV. So I need my RU and RV. So this is my partial derivative with respect to u of r, which is -4 sine v sine of u, and then 4 sine v cosine u, and then 0. And then I take partial with respect to v of r as well. And this gives me 4 cosine v cosine u, 4 cosine v sine of u, and then -4 sine of v. And now I take the cross product. So it's going to be the determinant of, we'll see if I can get this all to fit on here. Maybe. Okay. So I'm going to have negative sine. Oops, there should be a 4 in front of that. Negative 4 sine v sine of u. And then 4 sine v cosine of u, and then 0. And then 4 cosine v cosine u, 4 cosine v sine u. And then negative 4 sine of v. I will leave it to you to work out the details of this cross product, and I'm going to tell you that the result is negative 16 sine squared v cosine of u, negative 16 sine squared v sine u, and then negative, oh dear, 16 sine, that's a v, cosine of v. All right, it did all fit. And I do want to point out, if you are trying to fill in the details on your own, this piece right here, we use the sine squared plus cosine squared equals 1 identity. So very important here. We're actually going to use that a whole bunch of times here in just a second, because ultimately what we want is the length of n u of v. And this is equal to, well, the square roots of. This is going to be 16 squared. I'm not going to multiply that out. Sine to the 4th v cosine squared u plus 16 squared sine to the 4th v sine squared u plus 16 squared sine squared v cosine squared v. All right, now that looks like a huge mess, but this is our favorite identity. This is going to be equal to square roots of, and from here and here, I can factor out a 16 squared sine to the 4th cosine, oops, there should be a v there, squared u plus sine squared u. Always be on the lookout for where you can create these kinds of sums, okay? Like actively be looking, okay, what can I factor to get this? So that's it right there. Plus 16 squared sine squared v cosine squared v. Now, this is just equal to 1. And guess what? I get to do this again because I have a 16 squared, and then I have a sine squared inside of here and a sine squared right there. So I have a sine squared v. This leaves behind sine squared v. This piece is just 1, so we don't really care about it anymore. And then we have, well, after we pull out the 16 sine squared, I'm just left with cosine squared. So this actually simplifies down quite nicely because this piece here is 1. I didn't ever square the 16, so that was no work there. And then square root of sine squared, 16 sine v. And that's our length. So that's pretty great. So now we've walked through all of these pieces here, and we don't want to lose track of what our goal was, and that was to fill out this formula here. So let's go ahead and do that because I think we've got everything we need. So our double integral over that surface, f ds, which was equal to the double integral over our domain D, f of r u v length of NUV du dv. Let's start filling this out. So this right here, this is just 1 because we're told that f is 1, so there's nothing that we can really plug into it. Our double integral bounds on u were 0 to 2 pi, bounds on v were 0 to pi. And then we have this length of n of u of v. So 16 sine v is what I'm getting there, and then du dv. And then you can compute this integral from here. Should be pretty straightforward. It's just sine. If you kind of want a fun exercise, you can go back and look and be like, okay, well, what happens? I noticed that v was equal to phi, u was equal to theta. What does this look like? This guy right here is my rho. So it kind of parallels a lot of the similar ideas that we saw in spherical coordinates earlier. But one thing that I do want to point out before we move on to our next example was that, remember how earlier I said when F was 1, you're going to get surface area. So anytime that you have F equal to 1, you're going to get the surface area of the object that you were looking at. Well, the object that we looked at that we were integrating over was a sphere. Okay, it's a sphere of radius 4. Okay, rho equal to 4, which means that since if this function was equal to 1, and we went through and we took this integral, what we get is surface area. This value right here, when you're done with it, should give you the surface area of a sphere with radius 4. And that's one way, if you have a really nice kind of a straightforward shape like that, you can kind of check your work using some geometry formulas that you learned maybe in high school or something. So I don't know, you can plug that in to your calculator and see, make sure that that matches after you're done integrating it and stuff. So yeah, but anyway, that's pretty much how you go through this whole process. I have one more to set up for you. Okay, so in this example right here, we're going to look at S equal to x, y, z, such that z is equal to x squared plus y squared, and z is less than or equal to 49. Okay, and the function that we're going to integrate is going to be f equal to y squared x. All right, well, this integral is equal to double integral over domain D, f of r of uv, n of u v du dv. Okay, now this surface right here, because we have x squared and a y squared and just z, we're going to want to use cylindrical coordinates. So we're really just going to use a lot of the same identities that we did earlier. Remember that our goal is to replace x, y, and z in this case, because we want to just have it in terms of u and v. We're going to use the standard x equal to u cosine of v, y is equal to u sine of v, and we're told very specifically here that z is equal to x squared plus y squared, which working with cylindrical coordinates, that's going to be r squared typically, but in this case here, we've replaced r with u, so it's just going to be u squared. Okay. Again, like I said earlier, you're welcome to stick with the standard r and theta if that is what you're a lot more comfortable with. It's nice to keep it in terms of u and v sometimes because we've also got the r floating around there as well. So it's something to be careful with. So, but I'll make a note here. So r is u and theta is v. Okay. Yeah, so I think we're ready to kind of swap something out. So r of uv is equal to, and now I just got to place my x, y, and z components. And then u squared. And then, well, what are my bounds? Okay, well, we're told that z is equal to u squared, which is less than or equal to 49. So that means that u has to be less than or equal to 7. But because u is acting as our radius, we also need it to be greater than or equal to 0. And then because v is acting as theta, and because we want the full surface, we're not given any restriction on this surface right here, if we want to kind of see what it looks like, it's just a paraboloid. It looks kind of like this. So it's kind of bowl shaped, and we want it to go all the way around the circle. So v has to be between 0 and 2 pi. Okay. I'm going to go ahead and swap over f of r of uv, since this time there's actually something to plug in. This is going to be equal to, I'm looking at these guys right here. My y squared is going to come from u sine of v squared, and then we have u cosine of v going in for x. So I get u cubed sine squared v cosine v. Okay. Yeah, okay, so that's pretty much it for f. Now we got to start working with this piece right here, and I'm going to get a new page to do that. So n of uv is equal to ru cross rv. So r of u is equal to cosine v, sine of v, 2u. And rv is equal to negative u sine of v, u cosine of v, 0. Now, I'm not going to write out this cross product here, but I'll just go ahead and tell you what the answer is, so we don't have to walk through all of those computations again. What you're going to wind up with is negative 2u squared cosine v, negative 2u squared sine v, and u. This means that our length of n of u of v is equal to the square root of, I'm going to have 4u squared cosine squared v plus 4u squared sine squared v, and then plus u squared. Yeah, okay. So this simplifies down quite nicely because I can factor out that 4u squared from both of these pieces here. Then we get the cosine squared plus sine squared equals 1 thing. And we're just left with square root of 4u squared plus, 4u to the 4th. These should all be to the 4th power, plus u squared. Which I guess if you want to simplify it down even further, you get u of 4u squared plus 1. But you don't have to. You can leave it as it is. That's fine too. All right, so now we're ready to plug everything back in. So I have my double integral over the surface f ds, which was equal to the double integral over our domain of f of r of uv times length of n of uv du dv. So these are our bounds on u and v, which we had said were, let's go back, 0 to 7 for u and 0 to 2 pi for v. And then f r of u was u cubed sine squared v cosine of v. And then this is going to be times u root 4u squared plus 1 du dv. Oh, and this guy is underneath the square root sign. And yeah, that's pretty much it. The goal with this one was really just to set it up. Maybe I should have written that down explicitly at the beginning. Don't evaluate this, please. And I think you'll find that more often than not, you're actually not able to evaluate these integrals just because you do wind up with all of these kind of strange pieces that pop out from taking the length of n of u of v, which was the cross product and all of that. So a really popular problem format is to just say, okay, set up the surface integral. And then for practical purposes, when this gets used in like physics and stuff like that, a lot of times you'll find that you throw it into some sort of numerical algorithm to actually compute the integral for you. So you will, unless it's something that looks kind of like this one that we had earlier, sometimes they pop out really nice like this. This you should evaluate. This you should not evaluate. So yeah. So yeah, that's pretty much it. That's our introduction to surface integrals and also, I guess, parametrizing surfaces. So hopefully that's been helpful, and I will see you guys next time.